Hey everybody, welcome back. Today I want to talk about correlation, specifically the correlation between two quantitative variables, and get us started on the basics of regression. Just as an aside, we're going to be talking about regression analysis for the rest of the semester, but this is a good time to get some fundamentals down. So a brief aside, kind of wanted to do a quick recap of all the tests we've been doing so far. A t-test is to compare a quantitative variable over two groups. If you remember, all the way back in the very beginning of class, we talked about quantitative continuous, quantitative discrete, categorical ordinal, and categorical unordered variables, right? So the t-test is for a quantitative variable to compare that over two groups using the averages of the two groups. ANOVA is to compare a quantitative variable over three or more groups, sometimes a ton of groups. Chi-squared test is to look for an association between two categorical variables, either ordered or unordered, but that is a chi-squared test for independence. Chi-squared goodness of fit test is to compare one categorical variable against some theoretical expected count. So that brings us to the correlation. Correlation measures the association between two quantitative variables. Now, a couple of brief extensions. In theory, you can find a correlation between 3 variables, 4, 27 variables, but it becomes pretty quickly uninterpretable. So people pretty much 99.9% of the time focus on just 2 quantitative variables. Measures the association between. There's a particular kind of association. It measures only linear association. And I will show graphically when that comes into play. The way the metric, is via the correlation coefficient. The other comment I will make is that fields have a lot of very specialized correlations. The one I will present to you first is called the Pearson correlation. And that's sort of the default when people talk about, oh, find the correlation between two variables. I'd say more than 90% of the time, they're talking about the Pearson correlation. Unless they name a particular kind of correlation, they probably almost always mean the Pearson correlation. It's an R between two variables, X and Y. All right. So the reason why I put these formulas down is so we can get an idea, just an intuition about what's going on. And there's a multiplication here. All right, so this is my X variable. This is my Y variable. So intuitively, we take each observation, we compare it versus the average, and then scale it by the standard deviation. We take the other variables ith value, we compare it to the average, and we scale it by the standard deviation. You should recognize that this summation over n times 1 over n, summation over n times 1 over n is an average. All right, so we're going to be taking and averaging something. What we're averaging, you will recognize that these right here, these two things right here, should resemble something. And they're sort of, I will call them pseudo z-scores. So this is the pseudo z-score for X. And this is the pseudo z-score for Y. Now, they're not actually z-scores, right? An actual z-score has population parameters in it, we have the sample statistic. So it's not actually a z-score. But a z-score, if you remember, does tell you if you're at the mean, it's 0. If you're above the mean, it's positive. If you're below the mean, it's negative. And it involves the standard deviation. So we get a scale, like we get a scaling effect that is picked up by that standard deviation. That makes this result unitless. So this is a number that is either positive or negative. This is either going to be negative or positive, right? Times, this is a multiplication sign in here, something that is either negative or positive. And so this correlation coefficient can be anything between -1 and 1. -1 is perfect negative association. One is perfect positive association. And 0 is complicated. So one of the one of the beautiful facts about the correlation is that we always know how large is large. Kind of like with a z-score actually. But because we're bounded between -1 and 1, if I tell you the correlation between something is 0.8, we know we're only, I don't know, what, 20, 30% from 1, depending on how we treat the entire scale. If I tell you the correlation is -0.8, we're almost at -1. If I tell you the correlation is 0.001, you don't have to ask me what we're measuring, like what units are we using? Are they microns or light years? It doesn't matter because the beauty of the correlation is that we're always bounded between -1 and 1. So you always know how large is large, how small is small. So intuitively, when x is above its mean, right, we get a positive number here. At the same time that y is above its mean, we get a positive number here. A positive times a positive makes a positive. And at the same time, when x is below its mean, y is below its mean, we get a negative times a negative. It's also a positive. So what am I talking about? Okay, here is my 5 observations. Here is y bar. Here is x bar. For these two variables, x and y are below their mean at the same time, right? For those two circled observations, this term is negative times this term is negative. Okay, so we get a positive. For these two circled observations, x and y are above their means at the same time. So we get a positive times a positive, also positive. The only outlier, if you will, is this variable, when x is below its mean, but y is above its mean. So here, x is below its mean times y is above its mean. This would produce, this right here, would produce a negative cross product. But because the final result is an average, right? We get a positive cross product, a positive cross product, and only one of them produces a negative cross product. So this entire correlation would be positive. I'm not going to bore you by doing a negative correlation the same way, but you will recognize that if I would need to fill in this quadrant up here with data, and this quadrant right here with data, then X is above the mean when Y is below the mean, and vice versa. So this cross product would be negative. Not that I'm not allowed to have data here, but the final result is an average. So it's essentially an average of this cross product of where each variable lies when compared to its mean. So I said -1 and 1 are sort of these perfect linear associations. And I said 0 is complicated. So let me draw some stuff for you. So this would be R is greater than 0. And, I don't know, something like 0.7. Of course, I don't, I'm going to draw it. But this in no way is a perfect association, but we have a positive association. R is like 0.7. What would it look like if R was equal to 1? Well, if R is equal to 1, then all these points would lie exactly on a straight line. And vice versa for the negative. Now, I said that 0 is complicated. Why is 0 complicated? Because this is an example of 0 correlation. Uncorrelated. No linear association. But what I'm drawing now is an inverted U. And this too would have a correlation coefficient of 0. But is it really uncorrelated? Tough to say X and Y are uncorrelated. It's tough to say that X and Y are uncorrelated here because uncorrelated really implies a lack of a relationship. So here, okay, yes, lack of relationship, of course. But here, I wouldn't call this lack of relationship. This is a very strong relationship. It's just not a linear relationship. We can take it a step farther. I'm not going to use it. Here's a sinusoidal relationship. Right? Sine curve. It's definitely incorrect to say that X and Y are uncorrelated because it's supposed to look like a sine curve. But that correlation coefficient, the Pearson correlation coefficient, will come up with a 0 in this case. So, like a lot of statistical descriptive terms, The correlation will tell you something. It will tell you whether your two variables are linearly related, and because it is defined between -1 and 1, if we start to approach -1 or 1, it will tell you how strongly linearly related your two variables are. But be careful about r equals 0. Because you could be in this case where you have no relationship at all between the two variables, or in this case where you just don't have a linear relationship between the two variables. It's clearly a relationship, it is just not linear. Okay, that's the Pearson correlation. There are a ton of specialized correlation coefficients. We simply don't have time to cover all of them. There's a couple of things worth mentioning. It is sensitive to outliers. And, of course, sensitive to departure from linearity. So there's another correlation coefficient. It's called the Spearman rank correlation. It basically performs the Pearson correlation on the ranks of x and y. So you take our two variables, we find the ranks, what is the smallest observation, what is the second smallest observation, what is the third smallest observation. And then we do the same thing for the second quantitative variable, and we perform the correlation between the ranks. And it turns out that the Spearman correlation, first of all, is infrequently used. But it picks up non-linear associations. So that should make us happy because a lot of things are nonlinear, and it is less sensitive to outliers. And this should make us happy. But why am I teaching you mostly the Pearson correlation? Because when people ask you for a correlation, what they really mean is probably the Pearson correlation. I think the Spearman rank correlation should be used more frequently. Why is it not? I frankly don't know. I know in SAS, this can be produced using ProcCore. I don't know in SAS how you would produce a Spearman rank correlation. It must be possible because it is a real correlation coefficient that in many cases performs better than the default correlation. I think that's all I want to say about correlation. You know, there's a couple of other things maybe worth noting. One is that we can perform inference on the population correlation, which is rho of xy, right? So the sample correlation is r of xy. The population correlation is rho of xy. So this means that we can get a p-value get a confidence interval to test. And we have a null and alternative hypothesis. I preach that to make your null and alternative, your null as informative as possible, and you may have guessed that unless otherwise specified, like over 90% of the time, if you're not told anything else, the null hypothesis is that rho will be equal to 0, and the alternative is that the rho will not be equal to 0. So if you see a correlation and a p-value reported, that's most likely what they're testing. If you see a correlation coefficient and a confidence interval reported, that is most likely what they're testing, right? If 0 is inside the interval, it is one of the plausible values for the population correlation between your two variables. If 0 is outside the interval, you can claim that your two variables are linearly associated, either positive in a positive way or in a inversely correlated, so that that correlation coefficient is negative. I think I've run out of things to say about correlations, and we can sort of move on to bigger and better things. It's a useful descriptive metric. It's a useful descriptive metric, but it is just that. It's a descriptive metric. But if you're following along, the standard deviation is a descriptive metric. But the thing is, you never know how large is large in a standard deviation. But in a correlation coefficient, you do, because we're bounded between -1 and 1. All right, moving right along. Regression. Regression. The big idea regression analysis. The big idea is to propose a process by which data, specifically the outcome variable, were generated. What is the process by which my outcome variable came to be? What is the data generating process? So the way we write this out, we have our outcome variable. So this is the ith observation of the outcome variable. And you will have recognized this symbol, right? It's distributed as normal distribution. Now I'm going to color code a couple of things. There's a mu and there's a sigma. And now pay close attention to these two subscripts. So before, we've written things like this. Whoops. That some variable x is normally distributed with some mean mu and some standard deviation sigma. But now we're allowing the mean. Now we allow the mean to vary with each observation. Now, you will also notice that there is not currently, or typically, there is not typically a subscript for the standard deviation. So the standard deviation is assumed to be the same across all n observations. Each of my response values came from a normal distribution where the mean varies with observation and we have a common standard deviation. The technical word for this common standard deviation is stationary. Stationary standard deviation. Then, of course, the mean is not stationary because we're allowing it to move around. Okay, this alone is just math. There's nothing really all that interesting until we write an equation for this mean. Right now, we want to propose a process by which data were generated, and then we can make inferences about this process. We can test certain aspects of this process. So we write an equation for how the mean varies systematically. That's the key word. We want to write an equation for how the mean varies systematically. So we usually write something like this. All right, there's my ith mean. And it depends on usually two things. Alpha plus beta. You know what? I'm going to color code. Forgive me. Alpha plus beta xi. Again, track the subscripts. The ith mean depends on the ith x variable. And you remember that if yi is my ith outcome variable, then xi is my ith value of the explanatory variable. So it is useful to read the board from the bottom to the top. We measure some explanatory variable, and using this equation, alpha plus beta x, of course, this is the equation of a line. Right? Equation of a line. And by the way, alpha and beta are estimated from the data. So we measure some explanatory variable. Then its ith value is used to compute the ith mean. Then this ith mean gets entered into a normal distribution with a common standard deviation, and this normal distribution spits out our ith outcome variable. We start from here. This is our process, right? It's a linear response, right? It's a linear function. The mean is a linear function of x. Once we have computed each mean, it gets input into this distribution. Now it happens to be a normal distribution here. with a common standard deviation, and it spits out our response. Now, we're almost always interested in these alphas and betas. An equation of a line means that these two things are called parameters, right? They're regression parameters. Alpha is an intercept, and beta is a slope with respect to x. I'm just going to color code because x is measured. Right? X is measured because you collect the data in your explanatory variable. Y is measured, you have collected data in your response variable. But what SAS is going to estimate is alpha and beta. Now, you know where I'm going to go with this, just to give you a small preview. It is exactly never that we stop ourselves at just a single explanatory variable. Oftentimes, you have two, heck, three explanatory variables. So you have beta 1, beta 2, beta 3. So you have measured your response variable. You have measured 3 predictors, 3 explanatory variables. You input them into your software routine. Alpha, beta 1, beta 2, and beta 3 are estimated from the data. And again, we read this board from the bottom to the top. Based on the values of our explanatory variables and our parameters, we compute the ith mean, each mean value. And here we allowed the mean to vary with each observation. So once we compute the mean, we feed it into this distribution. And now this distribution spits out our ith response variable, all under a common or stationary standard deviation. So this standard deviation is super important, right? If this standard deviation were 0, we would force all response variables to be right along that line. But that's not reality, right? We don't know this equation perfectly. There will be some error. So this is often called the error standard deviation. Don't worry about this for now. I want to focus on just having a single variable, but we will eventually get to multivariable regression. So what I want to do now is see what happens when our one predictor is categorical versus when our one predictor is quantitative. And I must say that in a lot of introductory textbooks, it is almost always assumed that your one predictor is quantitative because the language that is used is intercept and slope. But okay, let's roll with that. So, trying to keep my color coordination going. X is quantitative, that's my explanatory variable. Is quantitative. And on this side, X is categorical. All right, I'm going to write it a bunch of times because I really want you to remember it. Okay, my ith outcome variable is distributed according to a normal distribution. Now, is it always going to be normal? No, we assume normal for now. And when I say for now, that's for the rest of the semester. We will relax this assumption when we meet again next semester. But for now, I'm going to keep writing it, but we always assume that our response variable came from a normal distribution, where the mean depends on our observation, and we have a common standard deviation. It is exactly the same. The setup is exactly the same on this side. Because the only thing that is different is how we parameterize, right? How we parameterize this mean. What kind of process we propose for how this mean systematically changes with observation. Okay. X is quantitative, so that means that my mean mu is alpha plus beta X I. All right, and so the picture that people usually think about when they think about a regression analysis is, this is my measured data, so I'm going to use the black marker here. These are things that I have observed. Okay, here are all of my observations. What is fit is then a line. Right? That is what is fit through these data. This line has an intercept right there. And this is the alpha. By the way, in some papers, textbooks, YouTube videos, blogs, people can sometimes use beta 0 for the intercept. I like using alpha because it separates it from all of the coefficients that are associated with the explanatory variables. But if you read it somewhere else, don't be surprised if it's not alpha, if this is something like beta 0. All right, now we have a perfectly straight line. This perfectly straight line is the varying mean that is then plugged into this distribution. This line has a slope of beta, right? Beta is the slope. Rise over run, right? So this is 1 unit over beta units up. So beta is the expected change. Our line can be pointing down as well, right? So that's why I'm saying this as expected change. Right now, my beta is greater than 0. But I can just turn this entire thing 90 degrees. Beta is the expected change in the mean. It's very clear that we're parameterizing the mean here. It's not the actual variable itself. It's the mean of the distribution that has produced our response variable. Per 1 unit change in X. So this is the interpretation of this slope. Expected change in the mean per 1 unit change in X. we can get a p-value, we can get a confidence interval for beta, all to test the null and the alternative hypothesis that beta is equal to 0 versus beta not equal to 0. Remember, the null has to be informative, because if we reject the null, it has to mean something. So when we set the null as beta is equal to 0, under the null, the mean doesn't depend on x at all. So if we reject that, beta is equal to 0, we're saying that there is some relationship between x and the mean of y. If we fail to reject, we're saying that it is plausible that this beta is equal to 0, and therefore it is plausible that x doesn't affect the mean of y. It tends to be the classic regression setup, but I just want to take it a little step further. What if our x, still just a single x, what if it's categorical? What changes? Well, I can write this next step exactly the same way. Alpha plus beta xi. That doesn't change. But this x is now categorical. So it's either going to be, say, a 0 or a 1. Because categorical. This could be the control and the treatment group. This could be women who did not smoke, women who smoke. This could be transported from out of state, transported from in-state. Any categorical variable, any binary categorical variable. So, unlike this x that can take on, in theory, an infinite number of possibilities, here we just have to contend with 2 possibilities. So, what it means is we actually have just 2 means. Mi when x is 0, and mu sub I, when I said m, I should have said mu, when x is 1. So when x is 0, we get 0 times beta is 0 plus alpha. Just get alpha. When x is not 0 but 1, so we're talking about the other group, we get alpha plus x is equal to 1, beta times 1 is beta. Beta. So, what I'm leading to is it is no longer helpful to think of alpha and beta as an intercept and a slope. That language assumes that we have a quantitative variable. But now, alpha is the expected mean in the 0 group. And beta is the expected difference between the 2 group means. Alpha is the expected mean for the 0 group, and then beta is the difference between the 2 group means. What have I done? I have 2 group means. two population means, I've just recreated a t-test. Using regression analysis. I can do the same thing. I can find a p-value for my beta. I can find a confidence interval for my beta to test whether the difference between the two group means, the group mean for the 0 group and the group mean for the 1 group, are statistically significantly different. This null hypothesis doesn't change at all. Almost always, or 99% of the time, the null hypothesis is that the betas are 0, because then if you reject, you're saying that there is, in fact, some association between my explanatory variable and the mean of my response variable. I think this sets us up for some more exciting things than just a single explanatory variable. But for now, I'm going to shut it down, and I'll see you guys for an activity on Thursday. Thank you, guys.